Hi, I don't know what everyone's prerequisites are, but this is going to be a talk on topological data analysis. The only thing that I'm really going to assume you know is sort of basic linear algebra, things about like what a kernel is, what the image of a linear map is. Outside of that, the only real construction that might be unfamiliar is just if I give you a bunch of basis elements, there's a unique vector space you can construct over any field with those basis elements. So really, you can just think about like Rn if n is the number of basis elements I give you, if that's easier. Let's see, which button is it to go to the next slide? Right. So why would you want to use topological data analysis? Oftentimes, data can be very visual. If you look at, a plot of your data in 2 dimensions, say, and it looks like it's a circle with an empty center, that tells you something about what you're looking at. It might not be immediately obvious what it tells you, but it means that you're not collecting or taking observations in a very specific range of sort of your measurables. And that is telling you that there's some structural thing going on most of the time. The issue is when your data is very high dimensional, say, for example, and this is an example we'll get to, you're looking at observations of cancer, and you're looking at sort of the how prevalent certain proteins and other things are in someone's blood. This might be like 52 dimensional. You might be looking at all sorts of things, trying to find a correlation, especially if you don't immediately know what you're looking for. So this is one reason to use topological data analysis, because topologists have for years been having to deal with the problem of studying a very visual field, but oftentimes encountering spaces that, are higher than 3-dimensional, and therefore we can't really visualize them. And we've developed algebraic tools to help solve that problem. It's metric insensitive. What I mean about this is if you change the units that you're measuring something in, generally speaking, this isn't going to change its topology very much. It might change sort of the dimensionality. It might change the size of your data, but this is a continuous transformation. And in fact, since most unit conversions are just multiplication by some fraction, it actually is, provably continuous. There's no parameterization. What I mean by this is that a lot of statistical tools, you sort of have to look at your data and, sort of make a few, not arbitrary, but at the very least, not mathematically defined choices. This doesn't happen with TDA. This is kind of an up and a downside, because on one end, it sort of limits exactly how geared to your data your tool can be. But on the other side, you also don't have to make an arbitrary choice, which is often hard, and you also don't have to defend your arbitrary choice, which is 2 nice aspects of using it. Some downsides. Small topological transformations to your data are not going to really show up. There's a notion of homeomorphism in topology that just means an invertibly continuous transformation. This is technically not an invariant on that, but if you sort of wiggle the definition of homeomorphism a little, it ends up being so. And oftentimes it's difficult to interpret a real world meaning. Like for the example I gave you of data in a circle around the origin, it's sort of hard to intrinsically know what this means. And you have to sort of look at your real world situation to figure out what the topology is telling you. And here's the basic pipeline. I have 2 different descriptions of it. One I stole from Wikipedia, and the other is what I wrote. So you start with some data set, and you sort of build a geometric complex. This is the topology part. You're sort of giving it a geometry in some sense. And then you take this geometry, you turn it into something combinatorial. We'll get to what that means, but it's what we call a simplicial complex or a simplicial set. And then you compute what's called its homology and get an output. These are actually diagrams I don't love. The diagrams I'm going to show you, I think, are significantly more helpful. But this is sort of the basic pipeline. Sort of in more depth, you take data, you give it some sort of geometry, you assign some algebraic gadgets to it, and you get an output. I like this description a little more because there are actually efforts to do more than what I'm going to show you today and use general algebraic tools from algebraic topology to study these spaces, as opposed to just homology. So this is a bit limited, but this is more or less what we're going to talk about today. And so first, we have to understand a combinatorial model. Now, combinatorial can be a bit loaded in mathematics. What I really mean by this is we're going to take something complicated, like, I don't know, your 52-dimensional data set, and we're going to show that it can be built in some sense out of very well understood geometric objects. In this case, it's going to be called simplices. Simplices you should just think about as triangles and higher and lower dimensional versions of the triangle. basically like the correct generalization of a triangle. And I'll show you a picture in a second. Right. So here we have the 0 simplex. It's just a point. To get the 1 simplex, you just add another point and draw a line in between it. To get the 2 simplex, you just add another point and fill that in, and so on. The basic idea is you just add a point and fill in what's called the convex hull. And the other thing we want to remember is that we want our simplices to be ordered. And what I mean by that is this is going to be vertex 0 in the 0 simplex. This is going to be vertex 0 in the 1 simplex, and this is going to be vertex 1 in the 1 simplex. This will be 1, this will be 0, this will be 1, and this will be 2, or actually I think the normal convention is 1, 0, 1, 2, yeah. And then you just do the same thing here, where basically what I'm saying is you just add another vertex, and then that newest vertex is the highest number. So in the 3 simplex, the 4th vertex, or the 4th vertex or the 3 vertex, depending on whether you start counting at 0, is going to be the one you most recently added. And we want to talk about maps in between these, because this is going to tell us how we take a space and build it up out of triangles. I'm going to tell you how you're allowed to combine triangles. And so the basic idea here is that we want to take only very specific maps. In particular, I want vertices to be sent to vertices. So the only maps from the 0 simplex to the 1 simplex, for example, are going to be sending it here or sending it here. And we also want the order to be preserved. So the only maps from the 1 simplex to the 2 simplex are going to be sending this guy to this guy, this guy to this guy, or this guy to this guy, and then this guy to this guy. The idea is that like this number, this vertex is labeled higher than this vertex, and this vertex is labeled higher than this vertex, and that ordering has to be preserved. This is kind of complicated to remember. The only real intuition you really need to know about it is that what we want is one specific way of mapping this line into this line, and one specific way of mapping this line into this line. And fixing and ordering on our vertices does make it unique. And so these are the face maps. And so you can see, just like I said, 2 maps out of the 0 into the 1, 3 maps out of the 1 into the 2, etc., and so on to infinity. We also have degenerate maps. We're going to also have an order preserving structure on these. The way you should think about it is that if I'm mapping the vertices 0, 1, 2 to the vertices 0, 1, I have to get rid of this 3 somehow. And the only way to do that is to repeat one of the other vertices. So for example, if I want to repeat vertex 1, I'll send vertex 0 to vertex 0, vertex 1 to vertex 1, and vertex 2 to vertex 1 again. If I want to repeat 0, I'll send vertex 0 to 0, 1 to 0, and then 2 to 1. And just continuing on in that pattern, you get one less map at each level. These face maps are what I want you to really focus on, because that's going to be more important for our structure. Now, this is going to be a geometric model, but the algebraic model is given as follows. These are all very complicated relationships, but if you actually look at them and sort of stare at them and then stare at the picture in the last slide, most of them are pretty obvious, and you don't need to remember them for the details of this. I just wanted to make it complete. So a simplicial set is going to be a set xn for each natural number n, and we're going to think of xn as being the n simplices, or the n triangles, basically. We're going to have face maps that tell us how, if I have some triangle, I can get to each of its sides. So if I start with a normal triangle, I'm going to have 3 maps, one taking us to each of its sort of edges. Same thing with a tetrahedra. I'm going to have 1 map taking to each of the faces. And we're going to have the degenerate maps again. You might notice that the degrees are the opposite in this case. As you remember, the face maps were actually going to higher degree last time. This is because we care more about starting with a simplex and going to its boundary than starting with a boundary and going to its simplex. So these are the relations of a simplicial set, and once you give this data, you've given your data a sort of geometric structure to it. And so we're going to get on with how we do that, and it's going to be a lot easier once you see the pictures. So suppose we have some data set S. I say it's a subset of Rn. What I mean by this is that each observation is just a real vector of real numbers. So, you know, it might be like GPA and most recent test grade and I don't know, something else. And that might be your vector, and you might look at like 100 students, and then that's your data set. So given such a data set, there's no real geometric structure to this, right? It's just a bunch of dots floating in space. Well, what I can do is I can choose some distance delta And I can just draw a delta wide circle around each of these data points. And that's what's happening here. I've just thickened the data set a little so that now there's sort of this geometric structure. You can see that some points are sort of connected, this one's sort of off and not connected to any of the others. And this is giving us some sort of topology on our data. And we're going to use this to build a simplicial set like we want. And then we're going to be able to use all of the algebra that algebraic topologists have been working with. So next, let S be as before. S is our data set. I'm going to denote by delta S the thickened version of our data set for some, arbitrarily chosen parameter delta. And what we're going to do is order our data points so that it's easier to refer to them. And this is how we're going to build our set. And I'm going to show you a picture of how this works in a second, but this is just the procedure. So the first thing we want to do is we want to take all of our data points and just make them one simplices. So all of our data points are going to be vertices. Then every time two circles overlap in the last picture, we're just going to draw a line in between them. Every time three circles overlap, we're going to draw a triangle connecting all of them. Every time four, we're going to draw a tetrahedra connecting them. Every time five, we're going to draw a five simplex, etc., and so on. If the data set is finite, this completes in finite time. It's not particularly hard. In fact, the actual way you compute it is a little bit simpler and faster than this might suggest. But I don't want to get into the details of the programming. And here's our example, and after this, I'll stop for some questions. So this is a data set. We've thickened it with some parameter delta. And then we see that these 2 points have a little overlap here. So we're going to draw a line in between them. There's no point that has no overlap, but say there was a data point, right here where my mouse is, and I drew a circle around that, then it would just be a free data point over here, and it wouldn't have any lines if it didn't overlap with anything. And then if you look here, between these 3 data points, there's a triple intersection. So we draw a triangle, another triple intersection here, we draw another triangle. If I added a data point here and suddenly there were a quadruple overlap, you could imagine a sort of point coming out of your screen right where my mouse is, and that would be a tetrahedra in our picture. So you start with a data set, just a bunch of discrete points, you thicken it a little bit, and then you give it a simplicial set structure. This is the basic pipeline for how we take our data and we turn it into something that is more geometric. I guess I'll stop for a second for any questions. Question, why is it more convenient to consider this as a simplicial set instead of a simplicial complex? Right. For one, a simplicial set is a genuine generalization of a simplicial complex. Every simplicial complex is a simplicial set. And there's sort of, I think in general, with the model as I'm describing it now, it will in general be a simplicial complex, a genuine simplicial complex. Simplicial set is just a little easier to work with and a little more general, and I'm not sure whether or not there are any algorithms that would give you something. Don't you need to introduce an ordering on vertices of a simplicial complex to turn it into a simplicial set? I think you normally want your simplicial complex vertices to be ordered, or at the very least you use it sometimes. Like if you're computing the homology of a simplicial complex, oftentimes you do need to care about what order your vertices are in to get the orientation right and get your signs correct. So I don't think that's an extra piece of data. Any other questions? I'm looking at chat, but feel free to interrupt me as well. Okay, cool. All right. Next, we're going to describe another algebraic gadget. I know this is a lot to throw at you. What I really want you to take away from each of these are the slogans I've been saying. So in particular, from the last one, just keep this image in your mind as we move forward. You don't need to remember all the different details of a simplicial set if you're not familiar with these things. This is going to be another complicated algebraic gadget, so I'm just going to jump right into it. Okay, so what is a chain complex? It's a bit complicated, but we really do need it for our theory, and I don't want to black box things in this talk, so we're just going to bite and go through it. So for each natural number, we want a vector space Cn, and we want linear maps between them. So you just have sort of this chain of vector spaces all connected with these maps that I'm going to refer to as deltas, not because they're actually deltas, I think they're dels, but I'm just going to slip up and call them deltas, so I won't even try. And so we have these vector spaces, we have these linear maps going down and down and And we want one more requirement, and that's that if I start here, go here through the first map, and go here for the second map, I end up at 0. And if I start here, go here, and go here, I end up at 0. That doesn't mean I end up at 0 in here. Most of the time you won't, but I need to end up in 0 by the time I'm done. You can denote this as delta n circ delta n plus 1 is 0. I assume I got these indices right. You can also write it as this because the subscripts are obvious, because it's always just the next one, right? You can't compose like delta n plus 3 with delta n without, using the intermediate maps. And so now we're going to introduce some terminology. So if I take some chain in Cn, so if I start here and I take delta n and end up in Cn minus 1, whatever I land on, we're going to call that a boundary. We're going to call this the boundary map. And that just means that it takes something in here and takes it to something that we can call its boundary in here. There will be a geometric connection to the sort of sense of boundary that you're used to. And furthermore, if I take something in here and it ends up in 0 here, we're going to call that a cycle. That just means that anything that doesn't have a boundary is a cycle. So here's the terminology. These are the things I want you to remember from this page. The image of something under delta is called a boundary. Something that gets sent to 0 or something that doesn't have a boundary is called a cycle. And the boundary of a boundary is 0, or the boundary of a boundary is a cycle. A boundary as a cycle is technically the right way of saying that. And what this is saying, it's just a rephrasing of this thing here. It's saying that if I take the boundary and then take the boundary again, I'm going to end up at nothing. I'm going to end up at something that doesn't have a boundary. So are there any questions about this? Because I know this is complicated. All right. Now we're going to define homology. This is the last major algebraic gadget we're going to need, so just bear with me a little bit longer. So one thing that is clear from the last slide is that the image of one of the maps is a normal subgroup or a sub-vector space of the second group. And what I mean by that is, I think about all the things that get sent to 0 by one of the maps. We remember that going from one map to the next is always 0, right? So the image of that map is going to live inside the kernel of the second map. And that means that we can always take a quotient. So what we're going to do is we're going to define the homology of a chain complex at n to be the kernel of partial n over the image of partial n plus 1, delta n plus 1. So the right way to think about this is that this is everything that doesn't have a boundary, and this is everything that was a boundary. So we're looking at things that don't have we're looking at things that don't have boundaries, but we're not themselves bounding something. The right way to think about this, and the reason why you might have heard the slogan "homology counts holes," is that another way of picturing this is everything that could be filled in, and this is everything that is filled in. So we're looking at everything that could be filled in minus everything that was filled in. So we're looking for holes in our data set. And that's what homology is going to count for us. You just have to take it on faith from me that the maps from the original chain complex also induce maps in homology itself. And this turns homology into a chain complex. You can do this on your own. It's not that hard, especially if you're familiar with all of this terminology. And here's the slogan again. We want things without boundary that are not themselves bounding anything. And we're going to look at some pictures after I do a little bit more computation. So now what do we have? Let's take a second to think about sort of what we've created so far. I have given you data, and you can tell me now how to turn it into a simplicial set, right? We thicken it, we give it these connections based on the overlap of these balls, and then we get a simplicial set. I can also tell you, if I give you a chain complex, how to get homology. So the missing connection is how to take our simplicial set that we have right now and how to turn that into a chain complex. And we're going to do it as follows. And it seems complicated on this slide, so I'm just going to sort of describe it in words. For Cn of our simplicial set, we're just going to take xn, those n simplices, we're just going to make a vector space with them. So each of these n simplices are going to be considered distinct, linearly independent, and we're just going to make a vector space. So for example, an arbitrary element of CNX, if we have if we have 5 different triangles in CNX, then we're just going to take like this first triangle plus 2 times the second triangle minus 1/2 the third triangle, et cetera, and so on. So we're just going to have linear combinations of these triangles. It's a very abstract idea if you're not used to abstract linear algebra. But what it's really saying is it's just sort of taking collections of triangles with a little bit of extra information with these rational coefficients. The reason I choose Q is because it's easy, and I think this is in general what the algorithms use. You can choose any field, and in fact, you can generalize this if you are familiar with module theory. Whenever we have a simplicial set, we can define a map. So if you remember, the only other piece of data I need to define a chain complex is a map connecting them for each n. This formula right here will do the trick. It's an easy computation to show that this satisfies partial squared equals 0. But you don't really need to remember it exactly. I'm going to do a few example computations, but it's not entirely necessary to have this memorized at the moment. And one other thing I want to point out here is that these DIs are the maps from the simplicial set itself. If you remember, we have those face maps. And so what this is really doing is it's taking every boundary element of our simplex. So this is really the geometric intuition here, is we're starting from a triangle, we're taking each of its boundaries and sort of adding them together in some sense. And we're alternating signs because this makes this equation work down here. Okay. All right, before I do this computation, are there any questions about sort of chain complexes, simplicial sets, and turning them into chain complexes? Again, either feel free to interrupt or message in chat. All right. Okay. So we're going to show that the picture of a triangle or the picture of an open hole is exactly what you'd expect it to be. So basically what I'm saying is, if you've noticed, I put little arrows on here. This is just showing that 0 is less than 1, 1 is less than 2, and 0 is less than 2. This is the standard way of orienting a triangle. And the reason for that is I can keep adding triangles to this and the arrows can match up ad infinitum. If I tried to make it go all the way around in a circle, you would see that you can sort of construct problems. Like I can glue triangles together in such a way that eventually you can't make the arrows line up. But if I do it this way, it always works. And so my first claim is that if I take the boundary of this triangle, it is in fact an element of homology. That if you consider this triangle not to be filled in, that this is going to be an open hole. And here's how we prove it. A, B, and C are the sides of the triangle. I'll explain why this is a negative in a second. But a very direct computation just shows that this is in fact 0. So this is certainly going to be in the kernel of our chain complex. Again, this triangle is a 2 simplex, so this will live in C2. And the element that goes to 0 will live in H2 in homology. Why do we subtract C? Well, if I pretend this triangle was filled in and call it T, and I just do the computation as I defined it earlier, I take the alternating sum of the face maps, then I end up getting B minus C plus A, right? Because I start with 0, I ignore 0 and take this side. I start with 1, I ignore 1 and take this side. I start with 2, I ignore 2 and take this side. So that'll give you B minus C plus A, which of course is the same element as A plus B minus C, just reorder them. And now we're going to give some visual intuition because this has been kind of complicated. So the first thing I want to tell you is that, so imagine that the blue just means it's filled in. Imagine this was our data set. Imagine we gave it a simplicial set structure in the same way as before. This is just another way of visualizing an outcome of that. So this triangle right here is going to generate an element of homology. And what I mean by that is it's not filled in. So it's certainly not itself a boundary. But when I take the boundary of this triangle, when I take the delta map, it's going to send it to 0 by the computation I did on the last slide. So this is a cycle and it's not a boundary. So this is going to give us a generator of homology. Homology is going to see this hole in our data set, right? Now take this filled in triangle here, or yeah, there we go. Take this filled in triangle here. Again, if I try to take the boundary map on just the outside of the triangle, it's going to go to 0 by the last slide. That's still happening. But if I try to take the boundary of this inner blue thing in the one level above in C2, because this guy lives, the outside lives in C1, then I'm going to get exactly this boundary, right? So this triangle outline is going to be the image of the filled in triangle under the delta map. So homology won't see this because while it is kind of a hole, it's also filled in. So homology sees holes that aren't filled in and doesn't see holes that are filled in. Again, it's kind of hard to see from this visualization, but this would live in C3 because it's a tetrahedron. If you imagine that this was filled in, homology would just ignore it in the same way. But if you imagine that it's not filled in, that you can only see these blue things because they're on the outside, then this would be seen and it would exist in H3 in homology. And we would have sort of non-trivial things in two different dimensions. And then finally, I wanted to give an example of this guy. It's not hard to think about why this wouldn't even be in consideration for homology, right? Because I only care about things that, you know, are in the kernel of these delta maps, right? Homology is the kernel quotiented by the image of the previous map. But this guy's not even in the kernel, because if I just assume this is V0, this is V1, and this is V2, and I take the boundary map of this side combined with this side, I'm going to have vertexes left. This vertex will cancel out, but I still have a copy of this vertex and a copy of this vertex with sign stuff going on. I think this one will be negative and this one will be positive, depending on how you orient it. But basically what I'm saying is this guy generates homology. This guy might generate homology. It's unclear from the image. And this guy definitely is ignored by homology. And then this guy is ignored by homology as well. So let's think about what we have so far. I can give you data. You can thicken it and then apply the Victoris-Rips complex, which is just what I described earlier. It's adding those simplices for every overlap. And that gives you a simplicial set, often denoted as S set. And as you can see, I didn't have much room on the slide here. I can then use this simplicial set as a basis of a vector space to get a chain complex. And then I can take cycles and boundaries. I can take the kernel over the image, and I can give you homology. So the real pipeline is data to homology. And we've pretty much completed it at this point. I've told you how to get every one of these steps. But we're not done. If you remember before, the choice of delta is actually fundamentally important to what's going on here. If I choose, so for example, let's assume I have some data set. Let's take it to be easy. Let's say it's grades on the last test, grades from 0 to 100, and GPAs of my students from 0 to 4. This is clearly going to be a data set where points aren't really that far apart. So if I put delta equals 1,000, then all the points are within 1,000 units of each other. So it's not going to see anything. It's going to see my data as one big blob, and that's not going to tell us anything. At the same time, if I put delta equals like something very, very small, then all the points will still be disconnected, and we're going to be just where we started. We're going to have a completely disconnected data set, and the topology won't tell us anything. So how do we choose delta? Well, we're going to refer to delta as a resolution from now on, because it's telling you how finely grained the topology is. The solution is to be greedy. The solution is to actually choose all choices of delta at the same time. And this is going to be called persistence. So yeah, we're going to choose all choices of delta simultaneously. What I really mean by that is we're going to let R be a number so big that all of our data is connected. So 1,000 for the example I just said. And we're going to start with 0, and we're going to choose all the possible resolutions in between 0 and R. And we're going to take homology at each of those, right? So from the notation before, I didn't really point it out, but let's say XS, comma R is if S is a data set, we choose resolution R, and we make a simplicial set out of the data set and at this resolution. So just the thing we did before, except now I'm making the resolution an argument. We can then take homology of this, just like we did before. We turn it into a chain complex and take homology. And we can do this for each R in the interval, each little r in the interval. So this is going to give us an uncountable amount of homology, and that's obviously not very useful for a computer program. Right? There's no way you can handle an uncountable amount of data, right? So what we're realistically going to do is we're going to choose intervals in this, regular intervals inside the interval, and we're going to like take snapshots. So if you think about it as sort of a timeline, you can take a snapshot every 3 seconds, and that'll give you sort of an idea of what the actual persistent homology looks like. And if you think about it, because our data set is finite, there's only so many changes that can be observed. So there is some number of intervals I can choose such that it captures the exact same amount of information as taking all of the little r's. So what I mean by that is, um, there's only so many ways our data points can interact with each other. It could be, a billion, but that's still a finite number, which means that if I choose enough intervals, I will eventually get the whole picture, and choosing any more intervals wouldn't help me. But how do we process this data, right? Because what have I given you so far? I've given you, for each dimension of your data, so if we have a 52-dimensional data set, for 52 dimensions of data, I've given you a bunch of vector spaces. So I've given you a vector space for each dimension level. And not only that, I've given you that whole set of data at every time interval. So this is a ton of vector spaces. And to be honest, it's hard to picture and hard to use that. I mean, it is technically a finite amount of data. It is technically something that could be used, and actually remembering more about it can be helpful. But we're going to simplify things. Remember that a vector space is fully determined by its dimension, right, up to isomorphism. So all that we really need to remember is how big is the homology vector space. And that's exactly what we do here. So this is called a Betti number, hence the B. And so for each time resolution, and for each dimension, or for each dimension of the data n, we're going to just set B to be the dimension of the vector space we got by taking homology. And now what we have is just a bunch of integers that are graded by dimensions n and times r. And so this can just be showed in a two-dimensional bar graph. And that's exactly what we're going to do. So here is an example of what's called a persistence barcode. And the persistence is, of course, the term for changing the resolution and seeing what changes. So you can think about it as, how connected are things as we increase our resolution? What sort of holes persist in our data, and what sort of holes, vanish very quickly? Maybe they were just sort of, they were outliers as opposed to, meaningful holes in the data. And so the way you just draw these barcodes is you put the resolutions on the bottom. You put the different dimensions, you stack them on top of each other. And then for each integer value that this B can take, you just add another line and you show how long that line lasts. So this tells you, and you can look at this picture and sort of follow along, B0 is going to talk about just how many connections there are, or how many connected components there are. And as I increase this, it starts with like, I don't know, I don't want to count this, but like a bunch of data points. It goes slightly fewer. So you see like these numbers go slightly down. And then fewer and fewer and fewer until you have one connected point. So this is saying that, the large number doesn't last very long. The next number lasts a little longer, a little longer, a little longer. And eventually you only have one connected component. And that's what this long line is telling you. And this is what you expect, right? Because you chose the capital R to be so big that everything overlaps. So eventually everything will overlap and you will get this. Again, in B1, what we're looking for is we're going to be looking for different sort of holes in our data, and you can sort of see these show up and then vanish as like this hole shows up right here, and then eventually it's filled in right here. And then you can take higher and higher data sets. If you look at this, there's obviously significantly more than just double overlaps. There's triple and quadruple overlaps happening right here. I don't know why the original author didn't include these higher ones. I stole this from a paper. But yeah, we'll get to other examples eventually. Okay, so we're going to do one final generalization of this, and then I'm going to break for questions. So if you remember what I was doing, we were taking our data set and we were determining how far apart they were in Rn. We were looking at the distance between data points. Sometimes this isn't actually helpful, right? One example that we'll actually look at in a little bit of detail is, imagine I'm trying to do visual image processing, and there's a picture of me and then the like ocean behind me. So 2 pixels that might be very close to each other is a pixel right on the edge of my shoulder, and then a pixel that is beach. Those will be right next to each other. Distance-wise, if we just take those as lattice points in the real numbers, those 2 points are very close together. But that's not very helpful information. What we could do is make a distance metric based on the color of the data points. So because the blue is very different than the color of whatever I'm wearing or something, that's going to end up, having a bigger difference in topology. So really all we need to do is specify how different 2 points are. It doesn't need to be a physical distance between them, We just need some notion of how different they are. And that's going to be helpful to keep in mind as we look at a few of the examples. Okay, before I go into examples, are there any questions about the theory? Sorry, I know I'm breaking for a bit, but I've been told that you should break for a while when it comes to these presentations over Zoom because it takes a while to type questions. But I guess I will move on then. All right, so here's the first example and the first one I was ever told about. What they did here is they took occurrences of breast cancer and they looked at different expression levels of various. I don't want to get into terminology here because I'm not a biologist, but there were different biological signatures that could be measured. And they took a bunch of these, like a huge swath of them, totally unvisualizable data set. And they were looking for sort of common factors. And it turns out that when they did a topological analysis of this data, there was this big blob of cancers that were totally disconnected from all the others. It was very hard to tell this just from looking at it. But there was this, the topology and the homology could very clearly see a disconnected portion. And it turns out these cancers actually were notably different. They had a very different mutation rate. And they had a 100% survival rate, if I remember the paper correctly. And this is important to know. You want to know if your patient has this specific one, but it hadn't been discovered until someone had looked at the data through this lens. So this is telling us that there really is actually something that topology can notice that maybe other statistical methods can't notice. And you can find this paper on the archive, I believe, if you want to read more about it. Visual processing, this is what I was referencing earlier. Topology can be very helpful in wanting to know, what is connected or not. If I'm trying to take, there's an XKCD comic about trying to take a picture of something and having a program that can tell you whether or not you took a picture of a bird. Part of the issue that you want to have there is you want to be able to know like when one object starts and when another ends. Our brains are very good at this, but computers still struggle with it. But if you look at the connectivity of the data, if you look at sort of how close together a bunch of things are, you can very easily find connected components in your data. That's what topology is made for. So it really is well suited to a few different tasks. And this one was not on the archive. I think it was under a ResearchGate link, and I didn't have the ability to access it without using my VPN. But if someone's interested, I could probably end up getting it for you. Just message me. Okay. And then finally, this is something I made, and the reason I became interested in topological data analysis, it was for an extra credit project for a second-year algebraic topology class I took. And basically what I did is, so if you're trying to compare two drug molecules, you're looking at their organic structure, just like lines between carbons, between different atoms, right? You look at these skeleta, it's actually quite difficult graph theoretically to tell how similar they are. There's an algorithm called maximal common subgraph that can be used to do this, but it's very, very greedy. It's NP hard, if I remember the classification correctly, but that's not hugely important. Basically, it's just hard. It's very hard. However, topological data analysis is the groundwork is linear algebra, and computers are very fast at linear algebra. So you can use it to compare these drugs, and because the idea for me is there's an issue in pharmaceuticals where when a drug patent is about to end, a company can just sort of adjoin an extra molecule, an extra sort of entirely trivial part of the drug to the old version. They can repatent this, and they don't have to prove that it's better than the original. They only have to prove it's better than a placebo in order to be able to market and sell it. And so what they do is they just keep reintroducing their drugs as opposed to sort of allowing generic versions to take over as a way of sort of cementing this permanent patent that they have. And this is kind of an issue, right? Because we want the money that's being invested in drug research to be invested in, genuinely new drugs, not in potentially worse versions of drugs that already exist. And the nice thing about this is that most of the changes that are medically trivial also end up being topologically trivial. And so you can sort of tell the difference between a bunch of different drugs just solely based on what their topology looks like. And I think I have to switch my screen sharing now, but I just wanted to give a few more examples from this. So just bear with me while I switch my screen saving. I don't say that this is a particularly good example of topological data analysis. It's just something that I'm very familiar with because I wrote it. Okay. So here's the idea. We're going to take a molecule, and there's a different bond strength between each of these. The actual structure does actually affect the bond strength, but there's also sort of a standard list of bond strengths dependent on what's connected. So this oxygen double bonded to this carbon is going to have sort of a specific standard bond energy. And what I'm going to do is, instead of considering these parts to be close based on how far apart they are in the graph, I'm going to consider them to be close based on how strong their bond is. What that's going to allow me to do is, not only will it differentiate structure in these molecules, but it'll also differentiate the composition of the molecules. Basically, because some atoms are considered farther apart than others, and they are technically farther apart than others, what's going to end up happening is that we're going to see this connectivity show up at different time periods. So if I switch this N for a carbon, and obviously there's some like problems that happen if you do that, but imagine I just switched it out for a carbon somehow. You would see this connectivity happen at a different time, a different resolution than will happen with an N, because of the bond strength difference between carbon-carbon and this. So next, we're going to look at a few different ones that I investigated. So here's an example that I did and computed for my project. I took this, I think this is a caffeine molecule, if I remember correctly, and this was just something I drew in a molecule drawer. And then I just appended a single carbon to this guy. And as you can see, these are the three diagrams. This is the diagram for the caffeine molecule. This is the diagram for the almost caffeine molecule. And this is the diagram for oh, is this ethanol? Yeah, I guess it is ethanol. And as you can see, these two are very similar. There's a slight difference showing up eventually, but they're very similar. And this middle one is entirely different, the barcode you get. I know that it's a little small, but you can just see that the lines are completely different, right? And you can look at sort of more similar molecules. I realize this is kind of a trivial example, but it also highlights the theory very well. And this tells you a lot about the structure of your molecule. And it's very fast. It doesn't require you to do any like hard computation. It just requires you to, build a vector space and then compute some linear maps, stuff computers are very good at. And that just tells you what you're working with. It tells you what your molecules look like. So that was pretty much everything I had prepared. 45 minutes, not that bad. I might have talked a little fast, I don't really know, but I hope this was helpful to anyone who's interested in the theory. And I guess I'm going to stick around for a few minutes in case anyone has questions. But other than that, thank you guys for coming. But feel free to ask questions now and unmute microphone. Can I zoom in on the barcodes? I believe so, yes. Let me. Well, I guess because of the way I made them different, they're actually yeah, okay. So it might be hard to tell because these are large, but there's actually one more bar up here than there is here, if you count. And that's because I did add that extra molecule to the caffeine molecule. Jessica asks, do you know why trivial modifications end up being topologically trivial? I'm not a molecular biologist, so I want everything I say here to be sort of a citation needed next to it. But the general idea is, as far as I understand it, that one of the big things that matters when you're making drugs is that the actual shape of the molecule is related to a lot of the properties it'll have with how it interacts with your body. And things that have similar shapes are going to end up being topologically similar. I guess one caveat that is actually related to this question is, imagine I take this molecule, and then I take the same molecule, but I add 1,000 carbons going off in that direction. What'll end up happening is you'll see a big difference in like these there'll be more numbers of lines, but the more the resolution increases, eventually it'll totally be unable to notice the difference. So there are some limitations to the system. But in general, it should be able to differentiate molecules that are at all different, just because the number of atoms should be different, or there should be at least one bond that's different, which will change the connectivity at some level. So it should be fairly fine. I can't really think of an example where it would be totally unable to differentiate, unless there were two molecules with the exact same bond energies, but I don't think that happens. I know we have some people here who study organic chemistry more than I do, so please just message if I say something incorrect. Any other questions? All right, if not, I guess I'm just gonna end this here. I guess I'll stay on for a bit. I have no reason not to. I'll stay on until 12:50 if anyone has any questions, but thank you guys for coming. I'll probably try to do more talks in the future because this was fun. But yeah, thank you. What resources are good for further reading? That's a good question. So there's two ways to further read. I would argue that a lot of people who program in topological data analysis don't understand the math behind it all that well. And I don't think that's an insult. I think that you can actually do it without really understanding the black box of homology and how it works exactly, as long as you understand the intuition I gave. But if you want to understand more about the theory, you might want to read something. Either related to algebraic topology, such as Hatcher's book, Massey's book. Any introductory text on algebraic topology will have a much better done mathematical background. If you want to look at further reading, there were a few papers I showed. I'll try to find some way of sharing these slides with everyone, and you can find the papers in the slides. Those are always great examples of uses of topological data analysis. And then finally, if you want to look at, I mentioned earlier that there are other tools other than homology that can be used. This is sort of the first version of topological data analysis invented. I think that if you really want to learn more about that, there are a bunch of young grad students publishing papers in TDA, and you should be able to find all of that material on the archive. If you wanted anything specific, please message me. I'm sure I'd be able to find something. But those are the basic directions I'd take it in. Either look at more concrete examples. There was one that was finance related, if anyone's interested in that. Someone tried to do stock market predictions with topological data analysis. I don't really remember if that ended up being significant, but it happened, and it came up on my feed at some point, and I glanced at it.
I have a question, Max.
Yeah.
So your barcodes that you draw, those are only those are only showing the Betty numbers, right?
Yes.
Would there be a way to tell, let's say that your data was sort of just perfectly aligned, that you had some class in homology for in H1 for small values of delta, and then at the exact moment that that class goes away, another class in somewhere else in your data appears in H1. It seems like the barcode would just sort of see that as one continuous line, that H1 is one dimensional for a long period of time, but really that's maybe not reflecting the actual structure of the data, that you had some one cycle that disappeared and another one cycle that appeared. Is there any way to kind of keep track of that information?
Right, that's actually a good question. So the way that the actual algorithms work, you should be able to keep track of specific generators. You should be able to keep track of what elements are actually creating homology classes. So in general, what you could do, it might take some work to figure out what a nice way of visualizing this is. It's not my area. But you could take these generators and give them bars. So instead of having a bar for each Betty number, let me zoom in here again. Okay. Come on. All right. Instead of having a bar for each Betty number, what you could do is have a bar for each generator. And these generators appear and disappear in the way you described. They just eventually are connected or not. Mm-hmm. And you could have bars for each generator and signify generators. And if you actually cared about specific holes in your data, maybe you already knew something about the topology or connectivity of your data, this would actually be something very interesting to look at. I've never actually seen that done, but it should be theoretically possible. Everything you need is sort of there. So that's a good question. All right, well, I think I'm going to end this now. But if anyone has any further questions, I think most of you have some way of contacting me. Otherwise, I'll just send my email in the chat, and I'm going to put @uchi. It's @uchicago.edu. That's my email. If you have any questions, I'll check it eventually. But thank you all for coming, and I had a good time.
Good talk.
How do I end this? Oh, there we go.